All right, so to continue where we left off last week, we were talking about carboxylic acids and derivatives of carboxylic acids, and one of those derivatives is an amide or an amide, and an amide functional group is like a carboxylic acid, except instead of an OH connected here, you have a nitrogen. And in an amide, that nitrogen could be bonded to two hydrogens, an R group and a hydrogen, or two R groups. So we could have an R or a hydrogen here and an R or a hydrogen there. We do need that lone pair, and that's one of the things that makes an amide stable is the contribution of this lone pair through resonance. So I have three resonance contributors. This is obviously the major one. There's a minor one where the electrons swing up and give a positive on the carbon, and another relatively minor one where these electrons swing in to stabilize that positive. So these linkages are pretty strong, and we're going to see in a little while how these linkages could potentially be broken or altered, but they're relatively strong. So they're good for certain polymers like nylon, right? If you're going to create a polymer that can be made into ropes that will be relatively strong, you want its structure to be strong. You don't want it falling apart and breaking down. However, this linkage can be broken, so it doesn't persist in the environment forever like certain other plastics do. So it kind of has a nice middle ground design there, and nylon is made by an amine attacking an acid chloride, right? So we said acid chlorides last time. We described how great they are as electrophiles because we have all this electron density being pulled away from this carbon through both resonance with the oxygen and induction with both the oxygen and the chlorine. And the chlorine's p orbital doesn't have very good orbital overlap there, so the resonance contribution of the chlorine to stabilize that positive is quite minimal. And the chlorine is a great leaving group, so when the nitrogen attacks and pushes electrons up to the oxygen, initially that linkage or that intermediate will look something like this. Because the chloride is such a great leaving group, when the oxygen swings its electrons back down, it could push the nitrogen out because it does have a positive. And this is not the most stable intermediate because of the two formal charges, but oxygen's okay at stabilizing a negative, and nitrogen's pretty good at stabilizing a positive, given their relative electronegativities. Although they're both kind of small, so the charge isn't extremely stable. But when those electrons swing in, instead of pushing the nitrogen out a good deal of the time, they'll end up pushing the chloride out. And then the chloride would have to pick off a proton from the nitrogen because it has two here, and in the structure, once that linkage is created, there's only one proton. So sometimes a base is also added during this reaction, so it can be what picks off that proton to stabilize the nitrogen. And so if two of these connect and make one amide linkage, once two of these connect, on one end there's going to be an NH2, and on the other end there's going to be an acid chloride. So the acid chloride can react with another molecule of this diamine and continue to build a chain in that direction. Meanwhile, the amine on the other end of the chain can react with another acid chloride. 2, 4, 6, 2. And once that connects, then there'll still be another acid chloride on the end of the chain. So both sides of the chain can continue to grow. So this is a different type of polymerization than we saw when we saw free radicals. You recall when we made our polymer in lab 1 and looked at the polymerization using a free radical mechanism, that was a situation where the chain would only grow on one end as one unit of monomer was connected at the end, one unit at a time. Here, these can start making chains, and then since the ends of the chains remain reactive the whole time, those ends can start connecting to other chains that are already pre-made, or a monomer unit can connect one at a time. And so these things grow into chains from both ends of the chain. And you can also make polyester in a similar way. So if you want to make polyester, instead of a diamine, you would start with a diol. It doesn't have to have 6 carbons in between, but a nylon 6,6 is a very common type of nylon. So if I want to make a polyester, I would do the same thing, except for it would be the oxygen attacking. And we would also probably use a base to pick off this proton, and then instead of an NH group here, you'd have an oxygen. And then you'd have an ester linkage. So depending on the application, you might want an ester linkage here, you might want an amide linkage here. The ester linkage is easier to break. And we saw last time through hydrolysis with hydroxide, or even in the environment over a much longer period of time, water can come in and push electrons up, and then when they swing back down, it will push out this oxygen leaving group, so you can start to break the polymer down. So if you want a polymer that will be more readily biodegraded, so it won't build up in the environment, a weaker linkage might be a good idea, especially if that polymer doesn't have to be super strong and long lasting for whatever application you're making it. So there's a couple practical uses of some carboxylic acid derivative linkages, including the amide linkage that we're going to talk a little bit more about. So once you make the amide linkage, how can you break it? As we were saying, it's pretty robust linkage, and the process is not fast because it goes through relatively high energy intermediates, but using H3O plus and water as your solvent is usually how that's done. So you need a fair amount of heat to get over the high energy transition state and facilitate the kinetics of that process. But what would happen first is the oxygen would pick off a proton from H3O plus. So you could imagine the nitrogen picking up a proton. If the nitrogen were to pick up that proton, the structure would look like this. Have extra nitrogen there. And I'd have a positive charge. If the oxygen picks up the proton, which should be more likely, then I get the positive on an oxygen. But we've been saying for a while that a positive charge on an oxygen is not as stable as one on a nitrogen because of the lower electronegativity of the nitrogen being more willing to share all its electrons than the oxygen, and the oxygen being more electronegative with an extra proton, it will start to pull electrons away from this proton. It won't effectively share. So what makes this pathway unlikely and this pathway more likely is the resonance that the nitrogen can shift electrons in. So actually what we have here is not just a positive on the oxygen, it's actually mostly on the nitrogen, but there is also a resonance contribution from the oxygen. So the positive actually exists on spread out and split over both those atoms instead of just on one atom, and that actually is favored overall because of the resonance stabilization. So once that occurs, then a water can attack to shift those electrons up onto the oxygen. So I have water here with a positive and an H2. So far this is pretty reasonable. It doesn't require any high energy transition states. The next step is also pretty reasonable. So we have a positive on this oxygen. It's not the most stable situation. So another water can pick off one of these protons And so that'll give me this intermediate here, which doesn't look terribly unstable, especially since there's no formal charge. So it's pretty stable intermediate. There's some sterics though, because we got so much going on right around this one carbon, all these groups kind of repelling a little bit. So the next step is what's really hindering this reaction overall from going forward. And that is what would need to happen next to push out the nitrogen as a leaving group is it would have to be protonated. It can't just leave because that would create a negative charge on a nitrogen, which is really quite unstable. Especially under acidic conditions, there's lots of protons around, so it's more likely something will pick up a proton than it would to just pull electrons away. And that goes for both the nitrogen and the oxygen here. But the issue is, if you have extra H3O plus, which you do because it's a catalyst and it's going to be regenerated, especially in this step here where the water picks up a proton, since the nitrogen is here, it can pick up that proton. And that makes the nitrogen a good leaving group. And so either of those oxygens can swing electrons in and push that nitrogen out. And then this nitrogen is a pretty decent base, so it would pick off that proton and give the products. The issue here is the fact that we've got this positive formal charge throughout is relatively unstable in some instances, especially when there's a lot of sterics going on. And this nitrogen can also attack here instead of picking up that proton and push electrons up and go back. So we also have an equilibrium. And I was focusing a minute ago on the kinetics, and the kinetics actually aren't as bad as I was thinking in my mind for a moment. The issue here, I think, is more the thermodynamics. Because the nitrogen is better at resonance, it contributes more here, and that stabilizes the reactant. The oxygen here is not going to contribute as much into that, so it's not going to be as stable as a product. So generally, amides are more stable than carboxylic acids, and that creates a situation where the reaction is going to favor the reactant side. However, since this NH3 is also a pretty decent base, it should be able to pick off that proton and create a relatively stable positive charge in the end compared to the H3O plus that we started with. So also, it was incorrect a moment ago when I said that the H3O plus is a catalyst. It's not a catalyst here because it's not regenerated. If water were picking up this proton to regenerate H3O plus, I could treat it as a catalyst, but since it's not, it should be the nitrogen that picks up that proton. That means that probably in this case the equilibrium actually should favor the product side because the positive on the nitrogen is going to be a little bit more stable than the positive on the H3O plus. So even though the amide is more stable than the carboxylic acid, NH4 plus is going to be a lot more stable than H3O plus. So that actually really should actually help drive the equilibrium toward the product side. So this reaction is your best bet if you want to cleave or hydrolyze an amide and convert it back into the carboxylic acid from which it was derived. You can also do, we just showed that mechanism. So should the equilibrium favor reactants or products? Probably the products. Despite the product not being as stable as the reactant, the other product, as we said, with a positive charge is going to be significantly more stable. So entropy is going to favor both sides about the same, But stabilizing the positive on a nitrogen is going to be a lot more stable than on an oxygen typically, because the oxygen has more protons, so it'll attract the electrons in more strongly, and not providing it enough electrons is an especially unstable situation for it. And we showed where that comes from in the mechanism. You can also do this hydrolysis with NaOH, but that is where the mechanism is really extremely slow, and so that makes that impractical. So actually, I think I was probably thinking about that in my mind earlier. With the H3O plus, the reaction is product favored, and it goes forward. It's not fast because some of the transition states are pretty high in energy, but it should work. If you're using a base, you would then require the base to come in here and push electrons up. And if you used a base to try to do this hydrolysis, you get stuck here in this step right here. Because when the oxygens swing back down, the oxygen here is a much better leaving group than the nitrogen. Going through the transition state where the nitrogen leaves to start to form a negative on this nitrogen is going to be a lot higher in energy. It's going to happen way less often. So really it's just going to go back to the reactants almost every time. So that's where the kinetic issue comes in, where it won't go through the transition state that releases the nitrogen as a leaving group. So if we want to push that out, we can't use basic conditions. We really need the acidic conditions here in this particular mechanism for the cleavage of the amide linkage. So another reaction that amides undergo is with LAH, and we've seen lots of reactions with LAH. It's a pretty versatile compound. We know LAH has a very unstable negative, so it will deliver a hydride to alleviate that negative to almost any electrophilic site. We've seen it reacting with aldehydes, ketones, acid chlorides, carboxylic acids, and so almost any carbonyl compound will accept a hydride. So when the hydride comes in there and pushes electrons up, that gives me this intermediate. And if there were no leaving group at all, the negative charge would probably remain on the oxygen. But in this case, the oxygen itself is going to be pushed out as a leaving group. So normally we wouldn't really even consider that. And that's why this is kind of an unusual mechanism. If we imagine a hydride coming in and pushing electrons up, the way you'd probably instinctually draw that next intermediate is like this, with a negative charge on an oxygen. And then we would normally think, well, the two options here are for these electrons to either stay there and wait till something with a proton is added so it can pick up a proton and give us a product, or the electrons could swing back in and push out a leaving group, but we don't really have a good leaving group here. A carbon, a hydrogen, a nitrogen, they're all really small atoms that don't effectively stabilize a negative. So instead what will happen is, because the aluminum's positive charge, so this negative only results once we imagine it sharing. We can also imagine this situation here looking like this, so that the oxygen forms a negative when the electrons swing up there, and then the aluminum has a big partial positive on it. So that's kind of like an ion dipole attraction. It's almost like solvation, except it's not the solvent. It's this counter ion. It's really forming a nice strong attraction here. So instead of the oxygen swinging electrons back in and pushing out a leaving group, since we don't have a decent leaving group, what's likely to happen here is, since the oxygen is so strongly attracted to the aluminum, it can actually leave, and the nitrogen will swing electrons in and push out that oxygen. And so when the nitrogen swings in, they'll form a double bond, and the oxygen will leave. It'll go with the aluminum. That produces an iminium ion. And then typically when we use LAH, we use excess, specifically because we know some is going to react with water. We want to have enough to react with reactants, so we might even use an extra excess here so that we can have a hydride delivered to this iminium ion. So when that comes in, pushes electrons up here, then we get an amine. So the net reaction here is to convert an amide to an amine. We need excess LEH to do that. And so this step here is a little bit different probably from what you would predict or anything we've really seen. So you might want to take extra note of that moving forward as part of this mechanism. So then the last carboxylic acid derivative that we want to talk about in this chapter are nitriles. And nitriles have an R group bonded to a cyano group, also known as a nitrile group, where the carbon has a triple bond to a nitrogen. We talked about how to make nitriles earlier in the semester. We said typically since the Cn minus ion usually comes with the sodium or potassium counterion, it's just a spectator. That's really pretty cheap, it's easy to get, it's very poisonous, cyanide, you don't want to consume it obviously, but it's a great nucleophile because of the full negative on the carbon. So it's not as strong as some carbon nucleophiles like maybe a Grignard, because the nitrogen is really withdrawing through induction a lot of that negative over toward it. So really it's a formal negative on that carbon, but really ultimately it's only a partial negative because a lot of the electron densities pull away. So that really helps to stabilize that negative. But still, a carbon is not good at holding a negative because it's such a small atom, it has a large charge imbalance there. So we would expect the carbon to attack here and push out the leaving group. That does require the site of the attack to be either primary or secondary, because we know if it's tertiary, there's too many R groups, it's too crowded for that to work. So if you have a primary or a secondary carbon that you want a nitrile to attack and there's a leaving group there, the nitrile can come in, push out the leaving group in an SN2 reaction to give you this carboxylic acid derivative. What makes it a carboxylic acid derivative is that the carbon is at the same oxidation number when it's part of a carboxylic acid as it is when it's part of a nitrile. Another way to make nitriles is by treating an amide with thionyl and usually a base. So to avoid the production of HCl, pyridine is usually added because the nitrogen with a positive is much more stable and much weaker as an acid compared to HCl. So we would add the pyridine here in this reaction to help facilitate the mechanism. So what's going to happen here is this oxygen with the large partial negative is going to attract to the large partial positive of the sulfur. And the nitrogen's lone pair is going to help facilitate that attack because it can shift in through resonance. So if that shifts in and pushes the electron pair to the sulfur, this really doesn't even exist as a pi bond anyway because the orbital overlap's not very effective. So really this thionyl molecule, as we said before, mostly looks like this, where you have a positive formal charge there. And so that sulfur is really very electrophilic. It very strongly attracts in a pair of electrons. Then this oxygen that's negative can swing back in, or you don't even really have to show that again because the p orbital overlap between oxygen and sulfur is pretty minimal, and the double bond that forms is not a major resonance contributor. But a chloride is a great leaving group. So if a chloride leaves, that's going to produce the next intermediate. And then the base, this is where the pyridine would be involved, would pick up this proton to stabilize the nitrogen's charge. And then another molecule of the pyridine, which is why we need 2 moles of it, is going to pick off a proton to swing electrons in to make the triple bond, and that pushes this whole group out as a leaving group. What's nice about this as a leaving group is it has kind of a leaving group within the leaving group. When it leaves, the oxygen can swing electrons in here and push out another chloride. So the chloride leaving groups are one particularly stable product. The SO2 gas that forms bubbles out and can't really come back in and reverse that step. So that step's pretty much irreversible. It drives the whole equilibrium forward, and it produces a nitrile. So if you want to make a nitrile, you can use a CN- to push out a leaving group, or if you have an amide, you can use the Thino chloride with 2 moles of purity. So those are the 2 ways that you might be expected to recognize for producing a nitrile. But what about reactions of nitrile? So one of the main reactions that nitriles undergo that you want to be familiar with is hydrolysis with an acidic solution. So what happens here is this nitrogen's lone pair is somewhat basic. It can pick off a proton from an H3O+. So I'm using H3O+ and water here. When the nitrogen picks off a proton, electrons stay here on the oxygen. And that makes a protonated nitrile, which is a pretty unstable positive. Actually, it's not that unstable. The electrons from the carbon can shift toward it to really stabilize it pretty well through induction, actually. And so as those electrons shift toward the nitrogen through both induction and through resonance, that does put a fair amount of positive onto the carbon. And that positive will attract water in as a nucleophile, pushing the electrons onto the nitrogen. So then we would have a couple proton transfers occur. Obviously the positive on this water is pretty unstable, and the most likely thing to pick that proton off would probably be water, since that would be my solvent. That would give me an intermediate that looks pretty stable. No formal charge anywhere. So the nitrogen is still a basic site, and we would still have H3O+ since we regenerated H3O+ here. So that nitrogen could pick off a proton from the H3O+. That would give it a positive charge again. And then this oxygen can swing electrons in and push electrons over here. So that's really just resonance. So what we have here basically is a protonated amide. We just need a water to pick off this proton, and that will convert the amide into its deprotonated form or neutral form. You can't really stop here though, so it's not really easy to get the molecules to cleanly produce the amide and then not continue under the same reactant conditions where we just started, right? So we're regenerating the H3O+ here. And so, if we're putting it in to get this far and it's regenerated, it's still going to be there to continue the process. So this reaction here and the mechanism is what we just saw over here. An amide with H3O+ and water producing a carboxylic acid. And we said that's product favored because the positive is a lot more stable on the product side versus on the oxygen, despite the amide being a little bit more stable than the carboxylic acid. But the big difference in positive charges on a nitrogen versus an oxygen is a pretty big difference. So that process is quite product favorite through the mechanism we described. So over here are the steps necessary to get to the amide, and then under the H3O+ and water conditions, the amide would produce a carboxylic acid and NH4+. And again, that is going to be product favorite in the end because of the stability of the positive being much more stable on the nitrogen than on the oxygen. So in the mechanism, the nitrogen is protonated multiple times, and water acts as a nucleophile. Right, we just showed the mechanism. Right, the nitrogen has to pick up a proton here, picks up a proton here, and then water acts as a nucleophile in this step here, and then the proton transfers allow you to form the amide. And then as we showed on the previous slide, the nitrogen will pick up more protons, and water will attack and eventually push that nitrogen as a leaving group. And then it can act as a base, pick up another proton, and stabilize the positive. So we could also imagine this working under basic conditions, but I'm not going to spend a lot of time on this because it's not very likely to occur, because you've got a negative on an oxygen. So there's no H3O plus, that wouldn't be added till a second step. But we really aren't even going to get that far, because if this oxygen attacks, it would have to shift electrons to the nitrogen. So the OH would now be connected there. And these electrons swing to the nitrogen. Now the nitrogen has a negative charge. So we know the negative is a lot more stable in the oxygen than the nitrogen. So this first step already is very reactant favored. So this nitrogen could pick up a proton off of water. But this first step, producing such an unstable negative, means that the first step is going to go through a really high energy transition state to get to that nitrogen with the negative charge right here. So it's just not going to happen often enough to make the process practical. So even if it did form, it would be forming very slowly. And so it's not a practical way to produce a carboxylic acid. Right? We just showed how to do that. If you want to make a carboxylic acid from a nitrile, H3O plus and water is your way to go through the mechanism we described. What else can nitriles do? Well, they can be attacked by other nucleophiles, right? This carbon is a nice electrophilic site. The electrons are pulled away through induction and resonance toward the nitrogen. So any strong nucleophile like a Grignard, which would obviously have a magnesium, sharing electrons with the carbon, but the carbons can basically treat those electrons as if they're owned by the carbon. They're too much negative in one spot. The magnesium can't really attract them. To make its noble gas configuration, it needs to get rid of them. So the carbon would use them to attack and push electrons here. That would give me another iminium ion. And that is going to be a lot more stable as a negative than the carbon with the negative. So that process should pretty much go forward. And if I add enough Grignard, it should convert all these molecules into this iminium. Then what would happen is, in a second step, H3O plus and water would be used. So obviously, as always, we can't use any water or protons around the Grignard, because the Grignard would just pick up a proton. So that's why we have to do these in two steps. But the nitrogen would pick up a proton. And that gives an imine. And in chapter 20, when we talked about imines, we said those can be hydrolyzed with H3O plus and water. The same conditions we use to protonate it. So really, if you're going to do this reaction with the Grignard and add another carbon to this carbon, so now we've got one R group was already connected to that carbon. We're adding another R group in. So we're extending the carbon chain, building up the structure of the carbon. We really can't stop at the imine very readily, because the conditions we would use to just protonate it are also the conditions we would use to hydrolyze it. So just to remind you of that hydrolysis reaction. The nitrogen would pick up another proton from the H3O plus. So just to save space, I'm just putting H plus. I don't have a lot of space down here. And so that's going to give me protonated imine or iminium ion. It's got a positive here. That makes this carbon more nucleophilic, so water can attack there. Once the water attacks, now I've got a positive on the oxygen from the water that needs to be deprotonated. I get a carbanolamine. The nitrogen is less electronegative than oxygen. It's more willing to share its protons than oxygen. So it would end up picking up an H plus from another H3O plus. Now the nitrogen has been made into a decent leaving group. Because it's positive, it's going to attract these electrons even more. And so the oxygen can swing electrons in and push that out. And then the nitrogen would deprotonate there. And so that would give an H4 plus and a ketone. So this is a nice way, if you do have a nitrile that has one R group you want, to basically take that R group and carbon that used to be part of the nitrile, convert the carbon into a CO double bond, and install another R group. So that changes the structure a lot. And so in your mind, if you're doing a synthesis and you're starting with a nitrile and you want to make a ketone, you might not see the connection. So you want to do some practices with this reaction at the very least. So we just saw how a Grignard nucleophile can attack a CN. We can also imagine LEH attacking a CN. And so this is going to happen twice. Similar how we saw carboxylic acids reacting with LEH. So the lithium aluminum hydride, such a strong reducing agent with a very unstable negative. It's going to deliver a hydride, push electrons here. So now a hydride will be connected to that carbon, giving a negative. And then another hydride will be delivered. Because this negative is still quite unstable, pushing more electrons to the nitrogen. And that's going to be pretty unstable because now it actually has a 2 minus. Now we'll hang out and then quickly pick up protons from the water as soon as the water's added to get those 2 protons connected to that nitrogen. All right, so that's a lot of new reactions that you might have to use in some synthesis problems. So we're going to do a little synthesis practice here, try to help you prepare for that. So always when we talk about syntheses, we talk about first checking the carbon skeleton. And what I would recommend in addition is to draw the hydrogen atoms anywhere near where it looks like changes are occurring. So you don't have to draw them necessarily all over the structure, but anywhere near the reactive site, the site where the reaction is occurring. That way you can see which carbons need to maybe pick up protons or lose protons or oxygens or nitrogens, and how are the protons being moved around? And that can help you think of what reaction might be occurring. In addition to how the functional group is changing. So you'll have to be familiar through practice or memorization with enough reactions to recognize how to convert one functional group into another. And we've learned a lot of new functional group transformations in this chapter. So here's a summary of them. Right, most of this is about ketones or aldehydes and carboxylic acids and carboxylic acid derivatives. Notice how many lines are coming out of the acid chloride. If you have a carboxylic acid and you use thionyl chloride, usually with pyridine, that will convert that into an acid chloride. And then once you have an acid chloride, there's lots of things you can convert that into. You could convert it back into the carboxylic acid, you can convert it into an anhydride, an ester, an amide, a nitrile. Well, actually not a nitrile, I got a little carried away there. You can convert it into an aldehyde or an alcohol. So there's lots of options there for a reactivity of the acid chloride. So that's one I wanted to point out. It's a key functional group that is often used as a bridge to get from common functional groups that aren't that reactive to other common functional groups. So there's a lot there for you to practice with. So here's an example. First thing I want to do here to try to determine what steps are necessary in the synthesis is to count the carbons. So I've got a ring, that's 6 carbons, plus one more, 7. Same ring, and one more carbon. So I'm noticing here the carbon skeleton's not changing. Maybe I want to draw out that CN group. Oops. There's no back button on this, unfortunately. So when I compare that carbon, which is the same as this carbon, I see I'm clearly adding a hydrogen. I've got to get rid of the nitrogen. I've got to replace that with an oxygen. So I need a reaction that will go from a nitrile to an aldehyde. So if I haven't practiced enough yet, I might consult this chart and see, well, what can I do with the nitrile? There's really only a couple of reactions. One that's not on here is the Grignard, but we know in general nucleophiles can attack there. But I definitely don't want a Grignard to attack. And I don't want a hydride to attack, because that would just give me an amine. It won't give me the aldehyde I want. So probably what I want to do is to hydrolyze this with H3O plus and water to form the carboxylic acid. Once I have a carboxylic acid, there are a couple options for getting to the aldehyde. I could treat that with LAH, which will give me the alcohol. Then how do I get from a primary alcohol to an aldehyde? I can use PCC and dichloromethane as a solvent. So that's one option. Go from the nitrile to the carboxylic acid to the primary alcohol to the aldehyde. Another option is after I hydrolyze the nitrile group and convert it into a carboxylic acid, I could use thionyl chloride and pyridine to make the acid chloride, which then could be converted to the primary alcohol and then PCC. Or, if you recall, we talked about this set of reagents here. I can go directly from an acid chloride to an aldehyde using this sterically hindered alternative to lithium aluminum hydride. So if you remember, what that has is there's a hydride attached there, but then there's three of these OR groups, And the OR groups are usually big bulky groups like terp-butyl groups. So if I have an acid chloride, what will happen here is the hydride will be delivered and pushing electrons up. Once that occurs, the negative will swing back down and push out the chloride. And that will give an aldehyde. Because the methyl group, or whatever our group is here, and the hydrogen are still there. So why do I need these bulky terp-butyl groups? When we talked about that reaction, we said, since this aluminum only has one hydride to deliver, once it's delivered, then the aluminum, which has a large partial positive, will attract to this oxygen. And it will remain attracted until a high polarity solvent like water is used to break that strong intermolecular force. So the aluminum will still have these big bulky groups around it. And that blocks another one of these molecules from delivering another hydride to the aldehyde. Right? We can't use LAH on an acid chloride and expect to get the aldehyde. The LAH will also deliver a hydride, which will push electrons up, and when they swing down, it'll push the chloride. It'll give an aldehyde temporarily, but then another hydride will be delivered there, and it'll end up, after it's protonated, producing an alcohol, which I could just oxidize back to the aldehyde with PCC if I wanted. But two steps probably aren't going to give as high a yield overall as one step, if that one step is a decent reaction. So using this more sterically hindered hydride reagent can deliver one hydride, which would cause the chloride to be pushed out to produce the aldehyde, and then that would stay there because there's too much sterics for another molecule to bring in another hydride there. And then typically water and H3O plus would just be used to break that attraction. And you don't even really need H3O plus in this case because there's nothing to protonate. So there are really two options here. One, add H3O plus and water, which will convert the nitrile into a carboxylic acid, which is kind of looking more similar to the aldehyde there. Then add LAH, which will reduce that down to the primary alcohol once some H3O plus and water is used to protonate that. Otherwise, I would just have an O minus after the hydride is delivered. And then I could use PCC to oxidize that. Alternatively, I could start with the same first step to produce a carboxylic acid. Then I could use thionyl chloride and pyridine to convert the carboxylic acid into an acid chloride. And then I could use the lithium aluminum hydride with the large bulky OR groups, followed by water to convert that into the aldehyde. So there's often multiple options. But to see them is going to require familiarity with the reactions as well as practice. So here's a nice helpful slide that shows some synthetic strategies. So we know generally if we have an acid chloride derivative where this is a decent leaving group, Then if we use excess of a Grignard, we can get the Grignard to attack once to push electrons up, then they'll swing back down and push out the leaving group, and then again to push electrons up, and then the electrons will stay there as a negative until some protic source is used to add a proton. So if you notice that you're starting with maybe one R group, we'll just call it X, and then the product has two identical R groups connected to that same carbon that used to be a carbonyl, it's a really strong sign that you need to use a Grignard, because if you use excess of it, 2 moles of that or 2 equivalents of that will be delivered to make 2 new R groups connected to that carbon. Recall the reaction where an acid chloride produces a ketone. This is the Gilman reagent. The R groups connected to copper, still more electronegative. They're still going to pull the electrons away from copper and deliver there to push electrons up, and when they swing back down, they'll push out the chloride. But then this is not strong enough of a reagent to attack this carbonyl. And so the chloride is really increasing the positive here, attracting the partial negative and the R group to attack. Here, now that the R group's there instead of a chloride, it's donating electrons through induction. And so the amount of partial positive here is much smaller, there's more sterics. So it's much harder, especially with 2 R groups, for the Gilman to come in there and attack, and we don't expect any further reaction to occur. Here's one we just learned today. Grignard attacking a nitrile, followed by H3O plus. And so that would extend the carbon chain, increasing the number of carbons. So there's some reactions here that in this chapter that we saw last week and this week that really give us a lot more control, where we can add R groups to carbons and extend the carbon chain. The reactions over here on the right-hand side extend the carbon chain by 1 carbon. So I've got 2 carbons to begin with. I'm going to add a 3rd carbon either by having a CN attack and push out the Br. So now I've got 3 carbons. And now we know also we can use H3O plus and heat to hydrolyze that to a carboxylic acid if we want. There's an alternative route to do the same thing if we use magnesium. That will convert this into a Grignard. CO2 is nonpolar, but it's a pretty good electrophile. There's a large partial positive there, so the Grignard can attack that, push electrons up. That would give a carboxylate here. There'd be a negative on this oxygen, so the H3O plus is used to pronate that. But the key thing is that the carbon of the CO2 is the 3rd carbon. So I've got 2 carbons in my chain, and one of those carbons is going to attack this carbon and that build 1 more carbon into the chain. So adding 1 carbon to the molecule at a time usually isn't the most efficient or economical way to build up a structure, but sometimes that's all you need, so you want to be familiar with those reactions as well. Now here's a particular application of that. So this is really quite straightforward. We've got 2 options here. So I notice there are 6 carbons in the ring, 1 outside the ring. And now I see, okay, I'm going to extend the chain by 1 additional carbon, and I'm going to make a carboxylic acid. So one option there is to use a CN minus to push out the bromine and then hydrolyze it. I'm just going to take a little heat, or I can convert that into a Grignard, have it attack CO2, and then simply pronate it to put that proton on. So those are the 2 reactions that we just talked about here. All right, so hopefully that helps you with your synthesis practice a little bit. At the very least, you might want to take a picture of this slide so that you have that for when you're practicing. It's also in the textbook, I'm sure. So I want to talk a little bit about spectroscopy for carboxylic acids. So from time to time, based on random chance, depending on what day of the week you have your exam, you may have to deal with the spectroscopy question at any point from now till the end of the semester. So you want to be familiar with some of the key details. So here we're seeing the carbon-oxygen stretching in the IR. Right? The IR is the one that starts at 4,000 and basically goes down to 0, and anything below 1,500 really isn't that useful because that's the fingerprint region. So we're concerned with the diagnostic region between 4,000 and 1,500. And if your structure has a CO double bond, which all of these do, that usually comes around 1,700. And you can see the specific area where that comes usually is between 1,650 and 1,750. The acid chloride is a little bit above that, but in general, I don't expect you to know the exact frequencies where these occur. So as long as you are aware that that would come somewhere around 1,700 or even potentially as high as 1,800, you should be good to recognize that as something important. So if I ask you to point out important peaks that you would expect in the IR for a structure, if the structure has a CO double bond, you definitely don't want to leave out the fact that it would have a significant, strong signal at around 1,700 somewhere. Or if I'm giving you IR data and anywhere between 1,650 and 1,750, I probably wouldn't put it above 1,750 just to keep things straightforward for you all as much as possible. If I tell you there's a strong IR signal in that area, you know there's going to be a CO double bond. If you see multiple signals in that area, there's probably multiple CO double bonds. So you may have an anhydride, or you may have a molecule that has more than one of these functional groups in it. And that also includes aldehydes and ketones. So any carbonyl really. What's important to note about carboxylic acids specifically in the IR is also the OH stretch. And if you recall, it's a little bit different from in an alcohol. So in a carboxylic acid, because there's such good hydrogen bonding between the large partial negative of one structure and the large partial positive of another, they're very good at lining up to form dimers, where two of these molecules come together. And so the large partial positive of one forms a nice hydrogen bond there, and the large partial negative of the other forms a nice hydrogen bond there. So that dimerization really weakens the covalent bond. And so that OH stretch centers out, the middle of that is around 3,000. So it might start as high as 3,300, but it's such a broad signal that it might go from 3,300 down to 2,500, and the center of that might be around 3,000 or maybe just above or just below. For an alcohol, we also see a strong broad signal for the OH stretch because it can also involve a hydrogen bond, but most of the molecules don't hydrogen bond as much. So the covalent bond is stronger, it takes more energy to vibrate, and so that signal usually centers out around 3,400. So it might start up closer to 4,000 and go down to 3,000. So it's a key difference basically in the quantity of energy required to stretch the OH bond. And so if you see a big broad signal that peaks out around 3,000, that's a good sign of a CO double bond or OH stretch, especially if it's combined with one of these signals for a CO double bond around 1,700. We know triple bonds in the IR, the stretching for that is usually around 2,200. And there's usually not much else in the IR in that area, so that's usually easy to pick out. And so that's basically the IR for carboxylic acids and carboxylic acid derivatives. So we want to talk about the carbon NMR a little bit. Carbon 13. A couple things you want to note. The carbonyl peak is usually around 160 to 185 for carbonyls that have a heteroatom bonded to them. So an OH, an OR, an O, CO double bond. So anhydrides, esters, amides, carboxylic acids. If there's a heteroatom here, meaning it's not a carbon, basically meaning it's not an aldehyde or a ketone, it's a carboxylic acid or carboxylic acid derivative, we usually see the carbon NMR show a signal for the carbonyl carbon, specifically in that area. It's above 150. If it's a ketone or an aldehyde, where the groups attached are just R or hydrogen, then that carbon, its signal is usually going to be closer to 200, so like 185 to 220 ppm. So it's a subtle difference, but it's something to look for. In general, if I ask you to tell me how many carbon signals there will be, and you see a carbonyl carbon, as long as you recognize the carbonyl carbon signal should be above 150, I won't necessarily expect you to say exactly where. But if you're able to remember that carboxylic acids and acid derivatives have slightly lower signals than aldehydes and ketones, it might help you with the specifics of your structure. The nitrile carbon 13 peak, that's the carbon that is triple bond to a nitrogen. That carbon signal, unfortunately, comes right in the area where we expect sp2 hybridized carbons of an alkene or an aromatic ring. So those are often hard to notice. But if you see an extra signal in that area, and it doesn't seem to match with the possibility of there being an aromatic ring or a carbon-carbon double bond, it could be part of a nitrile. And then you want to be aware that carboxylic acid protons, because they're so weakly bonded to this oxygen, the electrons are pulled away so much, they're so strongly deshielded, they come all the way down, usually between 10 and 12 ppm, depending on the specifics, usually a little closer to 12. Also be aware that if the solvent, the NMR solvent, has deuterium attached, which most NMR solvents do, depending on what the solvent is, it may be able to exchange that deuterium with the proton. And since this carboxylic acid is very acidic, well, not very acidic, but it's acidic enough where the oxygen can often pull electrons away and let that proton go to somewhere else, like the solvent, and then the negative charge of that oxygen can pick the proton up. So that can go back and forth and back and forth. Those proton transfer reactions have very low activation energies. They happen all the time. They're very quick. Once in a while, instead of picking up the proton, it could pick up a deuterium. So you may not even see the signal if you have a solvent with an exchangeable deuterium atom, like D2O or something. Right? This oxygen can give up this deuterium and replace it with the proton. If the solvent is the major component of the mixture, then I have it in large excess. Violet-Chatelier's principle should shift this equilibrium forward and exchange those deuteriums and hydrogens. And so I won't even see the peak around 10 to 12 if that hydrogen or proton has been replaced with the deuterium. So you want to be aware of that as well. All right, so here's an example giving you a structure. We want to predict the shift of all the carbon-13 peaks. So first of all, to do that, we would number the carbons. So I'll just start here randomly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 carbons. So will I necessarily see 10 signals? Well, in this structure I will, because there's no symmetry. But if there were any symmetry, I could find any two carbons that have the exact same environment due to the molecule symmetry, then they would only give one signal. Because, well, technically they would each give a signal, but they'd be in the same spot, so I'd only see one signal. So none of these carbons are equivalent to others. There's all, for each one of them, there's some difference in the environment because the structure is not symmetrical. So I'm going to have 10 signals here. Each signal needs a shift. I want to predict the shift, and that's usually between 0 and 50, between 50 and 100, between 100 and 150, or greater than 150. So you don't have to be too specific with the shifts in the carbon-13 NMR. So carbon 1 is part of a carboxylic acid. It's a carbonyl carbon, so I expect it to be probably between 150 and 185. I could say the same thing about carbon 6. I wouldn't usually expect that to be up around 200 unless it's a ketone or an aldehyde rather than a carboxylic acid or an ester. Carbons 2, 3, 4, 5, 9, and 10 are all part of an aromatic ring. They're all sp2. So they should each appear between 100 and 150. There's no symmetry on the ring. Seven and 8 are both sp3. So sp3 carbons come between 0 and 50 or between 50 and 100 depending on whether or not there's a highly electronegative atom directly attached to the carbon, which would cause it to be deshielded above 50. If not, it's usually going to be below 50. And so carbon 7 is another carbon away from this oxygen. So the oxygen is withdrawing electrons. So is this one, creating a large partial positive here. And that will withdraw electrons and create a partial positive there. But since there's no highly electronegative atom directly attached to carbon 7 or 8, I don't expect them to be deshielded enough to be above 50. So I expect both of those to be, they might be close to 50, but definitely below 50. So this one being allylic, or actually benzylic, it's going to shift it maybe around 20, 30, or 40, but it won't be above 50. We can say the same thing about carbon 7. So let's talk then about the proton NMR for this structure. So proton NMR, I would probably ask you for each signal, the chemical shift, the splitting pattern or multiplicity in the integration. So let's draw in the hydrogens and analyze them. So we'll call this one A. There's no proton here, no proton here. Let's call this one B. C. No proton there, nothing here, no proton here. Call this one D. Will this one also be D? Well, there's no chiral center anywhere in the structure that would create a spatial environment for this proton sticking out at me that would be different from the one pointing away, so they should be equivalent. Right, so typically protons on a CH2 are equivalent unless there's a chiral center creating a different environment for the ones that have different spatial positioning. So these two would be equivalent, these two would be equivalent to one another. Clearly they're different from one another because one is next to an aromatic ring, the other is next to a CO bond. No proton here, and then we have one here. So we have 6 signals. HA, HB, HC, HD, HE, and HF. So for HA, let's do the shift, splitting, and integration. So there's only one proton of type A, so its integration should be 1. It's on a carboxylic acid, so I expect it to be between 10 and 12 ppm. And I expect it to be a singlet. Right? There's nothing to cause, there's no neighboring proton anywhere to cause splitting. Even if there were a neighboring proton here, I still wouldn't probably expect it to split because it's going to be exchanging quickly enough where I'm going to see an average signal for it. If the solvent, so I want to look at the question here though, because if the solvent was given and it told me there's a deuterated solvent, I might expect that to be exchanged with deuterium. So I might see the signal, or I might not see the signal at all if it's replaced with the deuterium. HB is on aromatic ring, so I expect its shift to probably be between 6 and 9. What would its splitting pattern be? So when a proton is on an aromatic ring, it can be split by protons on the very next carbon away, or protons one more carbon away as we go around. It shouldn't be split by anything that's para to it. So anything that's on the ortho or meta position. So I would expect carbon B to be split by both C and F. If they're splitting B with the same coupling constant, I might see a triplet. If they're splitting with different coupling constants and one splits with a large coupling constant, the other with a much smaller one, then I'd see a doublet of doublets. I'd see one doublet, but then that would be split into two more doublets. And the integration there would be 1 because there's only one hydrogen of that type. HC, there's nothing to split it on any of these carbons here except HB. So that would also be aromatic, but it would be split into a doublet and it would have an integration of 1. D is on an sp3 hybridized carbon. So sp3 hybridized carbons usually, or protons on sp3 hybridized carbons usually give signals around below 5, somewhere between 0 and 5, depending on how close they are to something that's highly electronegative. So if I have an sp3 hybridized carbon, and there's a highly electronegative atom on that and a proton, that highly electronegative atom pulls electrons away so much, the proton's very deshielded. And so that adds about 2 to 3 ppm from where it would normally be, which is usually around 1 or 2. So these signals here are CH2 groups, which normally come around 1.2. There's no highly electronegative atom directly bonded to either of these carbons, so I don't expect a major shift downfield. But for this one, there is a couple options, one more additional atom away, so I expect that probably to add 1 ppm to that, or 1.5. And so that's going to end up giving me a signal probably between 2 and 3. It's going to be a triplet because HD is going to be split by 2 identical protons of type E. Using the n+1 rule, get 2 plus 1 or 3, which gives me a triplet for HD. It's going to integrate to 2. And then for HE, similar situation. It's not really close enough to these oxygens to be affected by them, but it is benzylic. Being 1 carbon away from an sp2 hybridized carbon usually also adds about 1 to the shift. So that one's going to be also probably between 2 and 3. And it will also be a triplet because it's split by the 2 hydrogens of type D. And then F would probably be split by B into a doublet, and with integrating to 1. And that one again is also on the aromatic ring, so 6 to 9. So I might ask you to try to describe where in this area the signals would be for B, C, and F. And so at this point, you do want to start to think about how these groups outside the ring are going to affect the protons on the ring through resonance to either shield them or de-shield them. Resonance is much more significant than induction when it comes to shifting electrons around. So what's going to happen here? Let's talk about B, C, and F. So this pair of electrons through a minor but significant resonance contributor can shift up here, creating a positive here, and that can shift electrons out of the ring, creating a positive here, which would shift over and create a positive here, which would shift over and create a positive here. So that means that HB and HF are bonded to carbons that have significant partial positives due to that resonance. But there's no partial positive formed on the carbon that HC is connected to here. So B and F would probably be de-shielded, and because of the positives attracting electrons. And that de-shielding would cause them to shift maybe closer down to 7, 8, or 9, the higher ppm side. And when we look at the other oxygen here, since it has lone pairs one atom away from the ring, they can actually shift into the ring through resonance, a minor but significant resonance contributor where they shift in and push this onto the carbon, or shift it around and push this onto that carbon, or that could shift around and push this pair of electrons onto that carbon. So the carbon that HC is on is actually shielded by the oxygen's resonance. And shielding it causes its shift to be a little bit more upfield. So C might be closer to the 6 to 7 ppm range, and B and F might be closer to the 7 to 9 ppm range. So I may ask you to rank protons that are on an aromatic ring within that range, depending on how resonance affects the shielding or de-shielding of the carbons that the protons are bonded to. All right. So we trudge forward to the next chapter. And we have only a couple more chapters to get through this semester. We're very close to the end now. See the light at the end of the tunnel. And the next section, chapter 22, is about enols and enolates. Reactions that take place at the alpha carbon to a carbonyl. So what does that mean? Well, here we have a description of what that means. So far, the reactions around a carbonyl that we've seen have involved breaking or forming bonds to the carbonyl carbon itself, right? We know a carbonyl carbon is electrophilic. A nucleophile can come in here, push electrons up. This is the carbonyl carbon. There are also a variety of reactions that can take place one carbon away, which is the first carbon away from the carbonyl, so that's the alpha carbon. So when we start using these Greek letters to label the carbons moving away from a carbonyl, we don't count the carbonyl. We've kind of talked about all the carbonyl chemistry. So that's like carbon 0. Carbon alpha or carbon 1, alpha, beta, gamma, obviously Greek letters 1, 2, 3. The first carbon away from the carbonyl, there's reactions that can occur there as well. And so that's what we're going to talk about in this next chapter. We're going to explore some reactions that take place at the alpha carbon. And what those reactions rely on is the fact that a proton on the alpha carbon is somewhat acidic. So what's going to happen here is a proton is going to have to be removed, one way or the other, if we're going to replace it with some electrophile. So that the basic thing here is Here's my carbonyl carbon. One carbon away is called the alpha carbon. There's an alpha carbon on both sides here. It's symmetrical, so it doesn't matter which side reacts. Get the same product either way. But we're going to have to replace a hydrogen that's bonded to the alpha carbon with an electrophile. That's a general theme for this next chapter. So the way that happens, there's lots of different details involved in that, obviously, that we're going to cover. So one way to do it, and the most common way, is probably with a strong base. If I need to get rid of this proton, because initially there are 3 protons here, and I'm going to replace one of them with an electrophile. So if I use a strong base, I'm just going to pick that proton off. Electron is going to stay behind. So what will that give? It will give a negative charge there. A negative charge on a carbon is quite unstable, but in this case, there's resonance because that negative charge can be spread out simultaneously over both the carbon and the oxygen. So there's a resonance contributor that has a negative on the carbon. There's another resonance contributor that has a negative on the oxygen because the electrons swing in to make a pi bond and push these up to create a lone pair. And so in reality, there's going to be resonance there, and there's going to be negative at both those sites, although there will be more on the oxygen because the oxygen is more electronegative to pull the electrons up there. Then an electrophile can receive these electrons. So what we'll see here as we go through is typically the electrons will swing in here, and it'll be the pi electrons from the carbon that attack the electrophile to make that new bond. Right, so once I pick this proton off, there's only 2 hydrogens left here. The next thing that needs to happen is just this pair of electrons acting as a nucleophile, picking up the electrophile to form a new bond. So this process can also work sometimes under acidic conditions. So if I have an acid here, I can get this oxygen to pick up a proton. That will make it positive. Now that that oxygen is positive, it's pulling these electrons away. And so now that it's positive and it's pulling these electrons up so strongly, its other resonance contributor looks like this. Which is a carbocation. And we know carbocations have the ability to form pi bonds if a neighboring proton is removed. So whatever the solvent, usually the solvent with H3O plus is water, so we'd have a water, pick off this proton, and that would give me an enol. Right, so that's an equilibrium, it can shift back and forth. But once this is formed, I've removed this proton from this carbon here. I've only got 2 protons left. So an electrophile can attract this pair of electrons. The oxygen can swing a pair in, and this pair can attack the electrophile. So then that can be converted to the product if there's a water to pick off this proton. So that would, H3O plus would be regenerated. And so we're using a catalytic acid. And depending on which side of the equilibrium is favored, that could potentially produce a high yield of the product. Right, so what is the difference here between these 2 routes? Well, the strong base is probably your first choice. There are a variety of strong bases to choose from, and we're going to see lots of examples of that throughout the week, throughout this week and next week for picking off the alpha proton to make an enolate. And an enolate's a great a great nucleophile because it has a full negative charge. It's going to be pretty good at attracting an electrophile and producing a nice stable neutral product. The catalytic acid is also a good option. The problem with this is that it's an equilibrium. Right? If my base is strong enough, if it's strong enough, that means it's really unstable. And if it's really unstable, and compared to the products, which would be much more stable, that process can be product favored. The stronger the base, the more unstable the reactant, the more the equilibrium will favor the products. In the acid catalyzed version, though, my most unstable substance is regenerated in the end. So I can't use that to control which side of the equilibrium is favored. In that case, it's going to depend on how unstable the electrophile is. If the electrophile is particularly unstable, usually this reaction will favor the products. So this is, kind of what we're going to be talking about in a nutshell. We're going to go into a lot more specifics here as we get through the content. So this enol-keto equilibrium, or tautomerization, we saw last semester. We saw it again this semester. And now we're going to focus on a little bit more detail. So without even worrying about the electrophile coming in yet, we're not even looking at synthesis yet. We would just want to understand the basic chemistry of what's happening here at this alpha carbon. So if I use an acid, we just showed how to do that. The carbonyl will pick up a proton, it'll become protonated. Through resonance, you'll get a positive here. A water can pick up that proton, shift electrons in, and produce this enol. So this is an equilibrium between the enol and the ketone. Obviously, equilibrium is very different from resonance. Equilibrium shifts back and forth. Resonance is instantaneous. Resonance involves, extended molecular orbitals where the electrons spread out in the molecular orbitals. Equilibrium is not just a molecular orbital where the electrons spread out over multiple atoms. Equilibrium is where the elements move and shift back and forth, and two structures have to go through breaking and forming bonds to get to one, and then breaking and forming bonds to get to the other. So that goes through reaction coordinate diagram and transition states. It's a reaction that can shift back and forth. Resonance is not a reaction. It's electrons spread out through molecular orbitals over multiple atoms. So in this equilibrium, depending on the structure, usually the vast majority of the molecules exist in the ketone form. So really what this means is the equilibrium usually favors the ketone form way more than the enol form. And that's because the CO double bond just inherently is more stable than a CC double bond. And so both structures have the same number of pi bonds and sigma bonds, but here the pi bond's a little bit more stable than the pi bond over there. And that's enough to dramatically affect the equilibrium in favor of the ketone side. There are some exceptions to that. So here's one. All right, so here I've got two ketones. If I do the tautomerization on one of them by, maybe let's look at the base mechanism for that, since we just looked at the acid one. The base mechanism would involve, if there's any trace amount of acid or base, it can go through one or another of those two mechanisms. So the base mechanism would pick off this proton. Electrons could swing in here and push up to the oxygen. And that would give this. And then whatever the conjugate acid of that base is, this oxygen can pick a proton up. So that would regenerate the base. When that oxygen gets protonated, it becomes an enol. So there are two reasons why this one favors the product, even though the carbon-carbon pi bond is usually not as stable as a carbon-oxygen pi bond. And one is there's an intramolecular hydrogen bond. The large partial negative, large partial positive, and there's 1, 2, 3, 4, 5, 6 atoms. So 6 atoms in a ring doesn't create really much significant ring strain, and bringing those two partial charges into close proximity forms an extra attraction that stabilizes the product that the reactant can't do because it's in, both of them are in the keto form. So that's probably the main reason why the product's favored. A secondary and also important reason is conjugation. Over here, the pi bonds are conjugated. So there's p orbitals on every one of these atoms, the oxygen, the carbon, the carbon, the carbon. All 4 of those atoms that are involved in the pi bonds have p orbitals overlapping side by side. So the extra p orbital overlap between carbon 4 and the ones I've labeled 4 and 5 here really helps to stabilize that. We talked about conjugation in chapter 17. Here, the pi bonds aren't conjugated. So they're isolated, p orbital overlap over here, p orbital overlap over here. There's no extended p orbital overlap, so I don't get the extra stable molecular orbitals that result when you have p orbitals overlapping on multiple atoms in a row. So those two reasons favor the product. Depending on the solvent, that's what determines the exact percentages, right? So if I have a more polar solvent, how will that affect this equilibrium? Well, a more polar solvent means that the solvent, whatever it is, if it's very polar, it will probably come in here and form some attractions to these charges. And that may break the hydrogen bond, the intramolecular hydrogen bond. And so that factor won't be there to stabilize the product anymore. So with a more polar solvent, we're probably looking at closer to a 30 to 70 ratio. And so the more stable CO double bond, pi bond being more stable than the carbon-carbon pi bond really increases the amount of reactants that are going to be present during that equilibrium. But the conjugation still favors the product side versus the reactant side. In a less polar solvent, one that can't come in and really bring much partial charge, well, the solvent's just going to be pushed out of there because these partial charges that are already on the structure are going to form a nice attraction. It's going to really stabilize that and make more of it form than would otherwise be there. So that's where we're looking at a 10, 90, 10 ratio. And then, you know, the ratio can vary in between depending on how polar the solvent is. So that's a pretty specific example. You know, you have to have 2 ketones 3 atoms away in order for this enol to have the intermolecular hydrogen bond and to create the conjugation. So the vast majority of structures don't have that, and in the vast majority of structures, the ketone is going to be dramatically favored when it reaches equilibrium over the enol. One other example where the enol is actually favored, another kind of unusual situation, is where the enol creates an aromatic ring. And we already know the name of this compound is phenol. We've seen that in the aromatic chapter we talked about. What makes the phenol stable is the ring is aromatic. And that is really very stabilizing compared to having a ring not be aromatic because there's an sp3 hybridized carbon, so it breaks up the conjugation. So technically there's the same amount of conjugation, 3 pi bonds conjugated here, 3 pi bonds conjugated here, but here the resonance and the aromaticity associated with the ring really stabilizes it. So this enol tautomerization dramatically favors the product side due to the aromaticity. So we showed this mechanism already. We said under an acid catalyzed situation, the ketone will pick up a proton, will produce this positively charged intermediate, and then losing a proton from here produces the enol. If you lose a proton from here, you just go back to the ketone. So this whole thing is equilibrium. It can shift back and forth. Each step is a proton transfer. So this process is very fast. It's not like I can form the enol and then try to isolate it and get an NMR on it, because the equilibrium is super fast, shifting back and forth. Proton transfer steps are quite fast steps usually. So that means that it's going to establish equilibrium quickly, and that's going to greatly favor the ketone side over the enol side, because I don't have any of the factors we looked at in the last two problems that could potentially favor the enol side. You can also do a base catalyzed tautomerization, which we just said with a base catalyst. We showed the mechanism for that. That involves the base picking off the alpha proton, or the proton from the alpha carbon. The electrons stay behind. That produces a negatively charged intermediate that's stabilized by resonance. And now here, either the oxygen could pick up a proton and produce the enol, or a carbon could pick up a proton to produce the ketone. And so again, if all the steps are proton transfer steps, it's going to occur quick. It's going to reach equilibrium fast, and the equilibrium is going to favor the side that's more stable. And a CO double bond's more stable than a CC double bond, as long as there aren't any extra factors like aromaticity or intermolecular, intramolecular hydrogen bonds or extra conjugation. So as we were just saying, this tautomerization, or shifting back and forth from the keto to the enol and back, you can't stop it. It's so fast because it's proton transfer. You're always going to have both those existing, depending on which is more stable, and it's almost always going to be the ketone. That's the one that's going to exist, although there will always be some small fraction of the molecules existing in the enol form, because it will reach equilibrium, which means you have to have at least something on both sides. When we look at the enol, since some of the molecules will be in this form, this is the major resonance contributor for the enol, but there is a minor contributor that forms when the electrons swing out to the carbon, right? This is very minor. But even though it's quite minor, it is significant. And if we look at this carbon, there is a little bit of red there. I don't know if you can really see it very well, but I mean, most of the red is on the oxygen due to its electronegativity, creating a large partial negative, and that's making it very red. But there's a little bit more red over here on this carbon than there is on the other one. And that means that this carbon, because of this minor contributor, which is still significant, is slightly nucleophilic. And we could take advantage of that and get that carbon to attack something and form some new carbon-carbon bonds. The amount of red here is pretty small though, right? So it's very weak. And we know very weak nucleophiles are not that useful. We want a stronger nucleophile if we want to force it to attack something and make some new bonds and get some interesting chemistry going on. So to make it a better nucleophile, all you have to do is add a base. If the base is strong enough, it will pick off this proton. Electrons can stay behind, be stabilized through resonance. And now we have what's called an enolate, which has a full negative. And the enolate is much more nucleophilic than the enol. Why is that? Because of the full charge that it has, right? The enol doesn't have an overall charge. It has a minor contributor with a small amount of negative on a site that makes that site weakly nucleophilic. The enolate has, since the base picked off a proton, a full negative charge. It's spread out between the oxygen and the carbon, and if we look at the resonance hybrid, most of the negatives on the oxygen, but there's a significant amount here. This is a significant contributor. They both have the same amount of total charge. And so that makes that carbon nucleophilic as well. Much more nucleophilic than this carbon, because this only has a tiny partial negative. This one has a pretty significant partial negative. And so we can get that to attack an electrophile and start making some new bonds. So there are two possible sites on the enolate that could attack the electrophile. There could be a carbon attack or there could be an oxygen attack, right? So these two are in resonance. Really what we're talking about here is the resonance hybrid, because neither of the resonance contributors actually exist. What exists is this resonance hybrid, and there are two sites that have a partial negative. So either one of those could pick up an electrophile. If the oxygen picks up an electrophile, I get this product here. If the carbon picks up an electrophile, I get this product here. So let's take a look at this reaction in more detail, and that's really what the quiz question for today was about. If you make an enolate, is it more likely to produce products resulting from attack by the carbon or attack by the oxygen? And we want to look at both the kinetics and thermodynamics of that question. So, if we're looking at kinetics and or thermodynamics, we're interested in the energies, and we want to maybe think about the energies of what's happening. So this question, basically we're already establishing that we have an enolate. So that's pretty much our reactant. Normally, we would start with a ketone. We would need an R group there. So we got some R group here. And we would add a base, right? To make an enolate, the base would pick off this proton. Oops. Oh yeah, the electron will swing up to the oxygen, and that would produce the enolate. So once we do, we have to realize that the enolate is in resonance. And so the reason I included this quiz question today is because I'm trying to prevent a common mistake that students make from occurring for each one of you. And that is, when I ask this question of students, or when students think about the enolate attacking an electrophile, what students often incorrectly say is that, well, the carbon enolate is a lot less stable, because carbon with a negative is a lot less stable than an oxygen with a negative. So students say, well, the carbon is higher in energy than this, and so if it starts higher in energy, it's more reactive. Well, that would be true and a reasonable thing to say if it actually existed. But it doesn't, because it's in resonance. So we know neither resonance contributor exists. What exists is the resonance hybrid. And the resonance hybrid is one structure with one energy. So if we've already formed the enolate, whatever the energy of the enolate is, it's at some energy value. I can't say that the carbon is like higher in energy and then the oxygen is lower in energy, because neither exists. What exists is the hybrid, and the hybrid has some energy value associated with it. So then the question is, when the enolate reacts with an electrophile, if the oxygen picks up the electrophile versus the carbon, what will the products be? If the oxygen picks up the electrophile, it'll be connected there. If the carbon picks up the electrophile, it'll be connected there. So we'll call this A and B. So when it comes to the thermodynamics, that's easier in this particular case, because thermodynamics is always about comparing reactants versus products. And if my reactant is this enolate that I formed and stabilized by resonance, it has a certain energy. The electrophile has some certain energy. So really the starting energy is going to be the energy of the enolate plus the electrophile that are reacting, right? Those are my reactants. The enolate's going to attack the electrophile and form a bond to it. Once it does that, if I'm interested in the thermodynamics, I'm interested in delta G. And delta G is determined by comparing the free energy of the reactants versus the free energy of the products. And I have two different products with different energies. Their entropies will be pretty similar, so that's probably not going to be a big factor. But a pi bond between carbons versus a pi bond between a carbon and an oxygen, there is a difference in stability. The carbon-oxygen pi bond is significantly more stable than the carbon-carbon. So if I'm just looking at the products, I can say the product B should be significantly lower in energy than product C because of the pi bond being more stable. So whatever the pathway is doesn't matter if I'm just looking at the thermodynamics. The thermodynamics is only determined by the value for delta G. And the delta G for the reaction that produces, oops, I don't know why I put C there, sorry, A. The delta G for the reaction that produces A is still going to be negative, but not nearly as negative as the delta G that produces reactant B. And so when it does reach equilibrium, it should eventually produce the product that's most stable. Assuming that reaction pathway can go back and forth and reach equilibrium, the equilibrium should favor the product that has the electrophile connected to the carbon because it preserves the more stable CO double bond. Right, so there's the thermodynamic argument for that. To discuss the kinetics, once, as I was saying before, sometimes students have an instinct to describe the different resonance contributors at different energies. And if one resonance contributor is at a higher energy, it doesn't take as much energy for it to get to the transition state. But that's not a good argument here because these don't exist. What exists is the hybrid, and the hybrid has some specific energy. So what I really need to look at, if I want to determine which of these products is favored kinetically, is what does the transition state look like and how likely are the collisions between the electrophile and the site where it connects. Right, so in one transition state I've got a connection between this carbon and the electrophile occurring. So I've got a carbon carrying that partial negative. In the other transition state, if the oxygen connects to the electrophile, it would be the oxygen that would be forming a bond to that electrophile. So the oxygen would carry the partial negative. So there are a couple issues at play here. One is the oxygen, we know, is better at stabilizing a negative, a lot better at stabilizing a negative than a carbon, even when it's only a partial negative. So we might expect pathway A to be lower in energy than pathway B. But, as we were just saying a moment ago, pathway A has a carbon-carbon double bond, which isn't as stable as the carbon-oxygen double bond. So we don't necessarily know which is a bigger factor, the ability of the atom to stabilize a partial negative or the stability of the pi bond, because B is more stable for its pi bond, but A is more stable in it having the partial negative on the atom that stabilizes it better. So those two factors kind of offset to some degree. There's also at play the molecular orbital. And when we look at the enolate, and the molecular orbital that's involved, what has to happen here is the highest energy molecular orbital of the enolate has to overlap with the empty, unoccupied orbital of the electrophile. There's going to be some orbital overlap. So there's an empty orbital here, and there's an orbital that has to overlap with that to make this new bond, and that also affects the stability of the bond. So I don't have a picture of it. I probably should have included one, but if you look at the shape of the molecular orbital on the enolate, there's actually a node here. And there's some electron density in that orbital around the oxygen, but there's a lot more around the carbon in that particular highest energy occupied molecular orbital. So in order for the electrophile to come in, it has to come in and overlap its orbital with this molecular orbital. It can overlap here and start to make product B through pathway B, or it can overlap up here and start to make product A through pathway A. There's more effective overlap when it comes in to the carbon though. So my best answer here is to say that because pathway B has a more stable pi bond and creates more effective orbital overlap during the connection of that bond, those factors are going to make pathway B lower in energy than pathway A, despite the fact that there's a slightly less stable partial negative there than there is in pathway A. If you look at this in detail, you find that the solvent can also impact that. And the stability of the electrophile can also impact that. So, if the solvent is really stabilizing the electrophile, it makes it harder for the nucleophile to attack. The fact that the oxygen is carrying a larger partial negative means it's more likely to attack if the electrophile is exposed and there's a strong attraction there. So I can get more of pathway A, and pathway A happens more often if those collisions happen to occur more often, simply because of the electrostatic attraction between the positive of the electrophile and the greater quantity of negative on the oxygen versus the carbon. So there are maybe some exceptions and specific conditions and circumstances that might change these energies a little bit in favor of one over the other, or facilitate one type of collision more than the other. But this is the general idea, and this is very convenient because what it allows us to do is to make this carbon, once we remove the proton to make the enolate, make that carbon bond to an electrophile, make a new carbon-carbon bond, or some other, maybe a halogen here, and that opens up a lot of interesting ways to affect the structure of the compound. So I know we're kind of over time a little bit. Just want to finish up here. I wanted to put a fair amount of detail into that though, because I know there was some controversy over that question in your answers in your Google Docs this morning. So when you have an aldehyde or a ketone, just want to point out, when I was an undergrad, this aldehyde seemed like it was special to me, and I figured maybe that was the most acidic proton on the structure, but it's definitely not, right? Because if a base picks off this proton and electrons stay behind, I would have a negative on that carbon. And that's not terrible because it is in a relatively compact sp2 orbital. And there is induction there to pull electrons away from the negative. But that negative being stabilized in a relatively compact orbital and stabilized through induction, orbital and induction, neither of those factors is as significant as resonance. So the reason that the alpha protons, or the protons on the alpha carbon, are going to be picked up rather than the aldehyde proton is because removing the aldehyde proton does not yield any resonance stabilization. So if the base picks off an alpha proton and electrons stay behind, that's much more likely, and we can measure that by looking at the pKa values, but it's the resonance stabilization that allows these specific protons to be significantly acidic. And we'll talk about the pKa values and quantify that next time. So just for practice, where are all my alpha protons? What are the possible enolates that can form? There's no proton here on this side of this carbonyl. This carbon is alpha to the carbonyl. No protons on it though, so I can't make an enolate there. Here, there are protons. There are 3 of them. So I could form an enolate there if a base were around to pick off this proton. There's my enolate. The electrons can swing back in and the carbon can attack an electrophile if I want to connect an electrophile to replace the proton that was removed. So there's one enolate that can form. Do I see any other alpha protons anywhere? So these protons are alpha to a ketone. These 2 protons are alpha to an ester, but still alpha, because for the same reason, if a base were to pick off one of these protons and electrons stay behind, the negative charge that will be formed there, there'll still be 1 proton left, is stabilized through resonance with the oxygen. So there's really 2 different enolates that you could form from that structure, just to point that out. All right, so there's a lot there. Finishing up chapter 21, getting into the first bit of chapter 22, so obviously practice up on that stuff. Let me know if you have any questions about it. And then on Wednesday, we're going to get deep into alpha carbon, enolate chemistry, and so I would definitely check out the videos and reading so that you can answer the quiz questions for Wednesday and be ready for that lecture. That is it. Unless anyone has any questions.